Hello again. So I've been seeing more videos about T Corona Borealis going to be going nova any day now. They can't actually predict when, but why exactly hasn't it happened already? Because so many predictors have been saying so for more than a year now, and we'll get into that. So I've done two videos so far on one on observing T Corona Borealis, like a public observing event, and the other one is all the different feeds that I subscribe to at no cost that tell me every new, maybe not true, observed thing from the Earth and in space from NASA, the General Communications Network, that's the GCN, and the notices of the American Association of Variable Star Observers, that's the AAVSO. And since T Corona Borealis happens to be a variable star, the Blaze star, that's I monitor it. But it's more than just visual. I get notices from GCN on gravity waves, X-rays, gamma rays. I have to filter through all this stuff. So I wrote some visual basic application software that runs in Outlook that goes in, knows how to read the emails, filter through all of them for the juicy bits, and then says, nope, not this time. It's a different thing in the sky, or it is there, but it's not bright enough yet. Now, if you're confused by all the names it goes by, all of these are the one and only T Corona Borealis or Corona Borealis, if you're into the Latin. Different forms of abbreviations to make it easier to write it down or search it. Imagine being a search engine in a piece of astronomy software, having to go, okay, what did they type in this time for the same thing? You can't force amateur. You can force professional astronomers to type in T Cor Bor, but amateurs will type in any of this stuff and the pattern matching just has to work. Now, this is T Corona Borealis, not to be confused with Tau Corona Borealis, which is a different star in the same constellation. Tau is actually a little brighter, not going to go nova anytime soon. So, assuming you haven't watched the other two videos that Broward Astronomy's put out there, T Corona Borealis is actually a binary star system. It has two stars in it. One is a small white dwarf that's past the end of its main sequence. It's collapsed down. And the other one is a red giant that's nearing the end of main sequence, so it's puffing out. The small, heavier gravitational item is feeding from the plasma coming off the red giant. And when the plasma builds up as a shell around the white dwarf, it gets to a certain limit. The plasma is essentially ionized hydrogen that it detonates kind of like a nuclear weapon. It does a thermonuclear detonation. That's what the nova is a thermonuclear detonation of hydrogen that has been drawn off of a large red star onto a smaller white dwarf until it just can't take it anymore. The white dwarf does not actually explode. The shell on the outside of the white dwarf is what explodes. When it goes bang like this, I don't know that you can hear it because vacuum of space, can't hear it in space. But for a limited time, it will grow bright enough due to this thermonuclear detonation to be naked eye visible at night for maybe a week, worst case a month. And then it will dim back down as the shock wave disperses the explosive plasma, back down where it's too dim to be naked eye visible again. It normally hovers around magnitude 9 or 10, but right now it's about magnitude like high 8 to 9. So they're saying that something's going to happen, but this process of blowing off the shell and then growing another shell and then blowing it off again, that cycle takes about 80 years to complete. So where is it? This is hopefully an improved diagram over the one that I put in one of the prior videos of where you can find T Corona Borealis. There's a background image. The background image there is from one of the astronomy packages that I use, and it's just a black line drawing of constellations. But if you follow on the right side, Ursa Major, the big bear, that's the Big Dipper. That's the arm of the Dipper coming out like that. And you follow the points of the arm of the Dipper down to a bright star called Arcturus in the constellation Bootes. And then you go up to where you see Vega in Lyra. That's another bright blue-white star. You sort of draw a line between Arcturus and Vega, and about halfway between the two, you'll see this little faint kind of piece of a letter C. That's Corona Borealis, the constellation. And then on the outside of the sea, sort of on the outside of the sea, that's where T Corona Borealis is. Now, if you want to know what's the orientation of the sea, in the sea itself, there is a bright star that should be naked eye visible called Alphecca, and it sits kind of at the bottom of the sea. So TCrB is on the opposite side. But if you want to star walk it, there's text of you take the Big Dipper stars to Arcturus and Bootis, about a little less than halfway between Arcturus and Vega and Lyra. Then near midway between the two, you'll find a faint C, and then you find Alphecca and the C, and then you come around to where TCrB is, but it is not naked eye visible at the moment. So you'll have to wait until it goes nova before you can see it. And since it's approaching magnitude 10, you have to have a good dark clear sky and a good, not a small end, low end amateur or novice telescope to see it. So what is this nova of which we speak? What's this process? Well, TCrB was first observed, if you can call the sketchiness of that observation, in 1866. And then they saw it again in 1946. And all they saw was, there's no star in that part of the sky. Wait a minute, look, there's a star that's bright now. And then the star went dim and disappeared again. So no star came in, was there for a while, and then went away. That's what they saw in 1866. And by 1946, they kind of knew what was going on, but it's the same sort of thing. So they only have two confirmed data points, 1866, 1946. Yeah, it's about 80 years. They know it's a nova by what we know now. So it's a recurring nova about every 80 years. But the actual sort of hints, the indicators of the event, in 1938, they saw a brightening. So with the telescopes that they had at the time, this is not amateurs, this is professionals with big telescopes, they could see it brightening. That was at about 72 years after the 1866 event. And then in 1945, they saw that little bit of brightness dim down. And then in 1946, 80 years after the 1866, is when it went nova. So it's brightening plus 2 years, dimming plus 1 year. And if you think about it, when the plasma starts accreting outside the white dwarf, it's going to get brighter. It's going to glow brighter. And then when the shell of that plasma starts to close out the white dwarf, it's going to get dimmer. And then when it gets really dense, you have your detonation. So you have brightening, dimming, nova. And they're saying that's the cycle. That's the precursors. That's what you should be looking for. So in 2016, not at 72 years, at 70 years, they saw it brighten. Now we have much better instruments and cameras and things, so we could have been seeing it no brighter than it would have been in early 1938 or 1937, but we can see better now. So, well, it was 2 years off. So it was 70 years, not 72. But they didn't know back in 1938. So maybe it is 72 years through the technology they had. And then in 2023, we saw it start to dim. But because we can see dimmer, we can see when it started to dim as opposed to it dramatically started to dim. So the dimming is off by -1 year. So the prediction of nova in 2024 or maybe early 2025, I think they just said that because they missed it in 2024, no nova yet. Our ability, technologically speaking, to see these brightening and dimming precursors is a lot better than it was in 1945. So we're just ahead of the game, so to speak. But if you just go out to the 80-year cycle that says the nova should occur, 80 years would be in 2026, which if you go back to the first presentation that I did on the subject matter, I was kind of hinting, if we take the 80 as the real number, then it should be 2026, not 2024, not 2025, but I could be wrong. So they are using these presumed predictors of brightening and dimming to predict it, but they're ignoring the fact that our technology is better now. So I think we're a little too early. But since then, they've kind of covered their bases by saying, well, maybe the plasma that's coming off the red giant onto the white dwarf is clumpy, and it's affecting our view, brighter and dimmer. I hear what they say. So here's some speculations as to why hasn't it gone nova yet? So each time the nova occurs, it blows off plasma from the system. So the white dwarf accretes from the red, and then the white dwarf blows the shell. And it not only blows the shell off itself, it also blows away some of that plasma that's hanging on the outside of the red giant. The red giant may be large, many, many times larger than the white dwarf, but it's not an infinite plasma supply. So the shockwave removed plasma can do one of two things. It can either bloat the red giant, like puff it up some more by stirring it up, or the red giant, having lost some plasma, can shrink a little bit. So if it shrinks a little bit, that means the distance to capture plasma from the white dwarf to the red giant is further. So it might take a little longer for the required amount of plasma to come over. Or if it bloats, if the nova event kind of oscillates the plasma around the red giant, it reduces the density of it. It kind of like puffs it up. And when it does that, it'll take longer for a sufficient quantity of the plasma to make its way to the white dwarf. Between the event affecting the red giant and the loss of plasma by every time, the shell, when it blows off, it doesn't give it all back to the red giant. It could blow it out 360 degrees by 360 degrees, so it could leave the entire binary star system, and therefore the total plasma left in the two-star system should slowly decrease, which means it takes longer to accrete to the level of detonation. So it could take longer over time. How much time, how much longer? I don't think anybody's evaluated that yet. But the one thing they do note is if you're a red giant and you're getting near the end of your life because you've lost enough of your bloated away plasma that gravity crushes you back down, that red giant is going to not nova, but supernova. When will it occur? Before or after Betelgeuse? They're the same kind of star. I don't really know, but yeah, eventually the eventual life end for the red giant is going to be a supernova. So another thought is the shell on the white dwarf may not be uniform. The plasma coming off of the red giant may be lumpy. It may be thin, thick, thick, thin. It may change over time as the white dwarf is rotating and the red giant is rotating. It may be that it can only suck off certain densities of plasma at certain times. That means that the shell arriving at the white dwarf is not of a consistent density. So it may take time for the plasma to uniformly create a thick and dense shell, has to level itself out. That may take longer. Or, unbeknownst to us, because the red giant was pointing away at the time, the red giant could have spit out, because the red giants do this stuff, it could have spit out a plasma ejection that was very sizable in the direction opposite our point of view. So while it was rotated away from us, it spewed out a bunch of plasma that we didn't notice, and therefore it denied the white dwarf that plasma. Because the white dwarf's over on this side, we're looking at the white dwarf, we're looking at the red giant, it spit it that way, Earth is here, so the white dwarf couldn't get that plasma, it lost the plasma, and therefore it'll take longer. But since we couldn't observe that, we don't know. And the other thing is, this is another one of those, it's taken longer because this is a two-star system towards the end of its life. Earlier on in its life, there may have been planets, asteroids, comets, all the normal stuff of a star system. And when these two stars started to misbehave, that kind of like broke up those planets, asteroids, and comets, and it produced debris fields. Now, both the white dwarf and the red giant have large gravity fields, and therefore they could have drawn in some of that material and it could block out the path. So let's say the white dwarf, which has greater gravity, is trying to pull plasma off the red giant, and a former Jupiter-sized planet that's been broken up gets in the way of that plasma coming off the red giant. That could slow down the accretion disk buildup. That's another speculation. But the one I like, which is if it's going to happen every 80 years, it won't actually be 80 years until 2026. That's the one I'm counting on. So in summary, the universe functions by a set of recurring processes. Some of them are very precise. So, for example, a neutron star that has got polar emissions and it's spinning very fast and it's creating these radio wavelength sweeps. Those sweeps are extremely regular to the tune of millions of a second or microseconds. And they're accurate enough in their pulsing that we can actually use them to detect gravitational waves, because the gravity wave distorts that emission coming off of the neutron star. And so in the microsecond pulsing, we can see billionths of a second variations, nanoseconds. So very precise. Some things are reasonably precise. For example, the rotation of the Earth is not precisely 24 hours, 23 and change. And the orbit around the sun is not precisely 365 days. It's 365 and about a quarter. So we have to introduce these artificial things because our technology is now far more accurate than nature is. So we introduce this thing called a leap second. You've heard of leap year. Every 4 years, February grows an extra day to keep the calendar in line with the normal occurrences of the universe. Well, that doesn't quite take it into account. A few more years after that, maybe every 10 or so years, we throw in another second in our Earth recognition of time of day clock. It accumulates fractions of a second until then, and then it gets kind of a burp point. And the WWV in Fort Collins, Colorado, at the top of the hour on that midnight going on to January 1st, won't go beep, it'll go beep, beep. It'll do 2. Throw in an extra second there. Some of these cycles do occur, but they move. So what time is sunrise and sunset? Well, it varies with seasons. The orbits of things around the sun versus the orbit of the Earth. When is Jupiter and Saturn going to rise? I don't know. Is it a morning star or an evening star? Well, it's not a star at all. Well, sometimes because it's on the other side of the sun or the near side of the sun, or the Earth is on this side of the sun or that side of the sun, relative to the other things in the solar system, the rise and set times will change, but they're pretty regular. And then we have the things that are very hard to predict, which are volcanoes and supervolcanoes. I've been to Yellowstone. Yeah, it's going to happen any day now. I don't know, but eventually. Earthquakes, massive earthquakes. Is California going to break off into the sea? Maybe soon, maybe not soon, but these things aren't predictable. And supernovas. They watch a lot of stars that are on the verge of supernova, but their ability to predict when a supernova is going to happen is fairly limited. There's a lot of precursors. The biggest precursor to within a day or so of a supernova is the gravity, and not the gravity wave, the neutrino detector in Antarctica called Ice Cube. Gets a big hit from a certain area and goes, okay, we've got a massive burst of neutrinos from this general direction. Do we know anything that's about going to supernova in that general direction? And then they'll tune all the other telescopes to watch it, because then it will go nova to supernova in other wavelengths. All the different observatories can watch. And then we have things that are supposed to occur every 80 years, but we're just impatient. Our technology improves. We can see things differently, but the behavior of physics is going to be the same. So when is it actually going to occur? Stay tuned. I'm thinking 2026, but I'm just an amateur. Okay. And then some links. T Corona Borealis is also known as the Blaze Star. I'll give you the 2 YouTube video links for Broward Astronomy that will show you the different presentations I did there. If you're really interested in understanding how do I get all these notices, NASA's GCN, the Variable Star Observers, and then what is a leap second? Does something jump up and down when it leaps? No, it just leaps time forward by 1 second. Comments, questions?
So, is the detection right? Neutrinos are going to be emitted first.
Yes.
And gravity waves, I guess, then, and then electromagnetic spectrum. But last time I was looking, I thought neutrinos were really, really hard to detect. Are they able to be detected sufficiently now that they'll see the neutrinos first? I think that's what you said, right? That they'll
Yes,
see the
yes.
neutrinos
We
first
we
and then
have
have
we
a
have
telescope?
we have zero ability to detect neutrinos directly. But what we can do is indirectly detect neutrinos. And the way they do this is they look for a particular kind of bluish radiation. And what that's from is if you have a tank filled with water, or as it turns out, dry cleaning fluid, either works, then when the neutrino passes through all those water molecules, which are fairly dense, the probability of a neutrino actually interacting with one of them has more to do with speed of light shock wave. And if you've ever looked into or looked at an image of a video, a nuclear reactor, a fission-based reactor, and you see the pile down in a giant tank of water, you'll see that the water is glowing blue. And that's because the particles, the neutrinos from the reactor, are interacting with the water molecules at a very low probability. But since there's a lot of neutrinos and a lot of water molecules, it creates a blue glow. It's a very dim blue glow. This is what they're detecting down in Antarctica. They have this observatory called IceCube. What they did was they melted giant holes, piles down into the Arctic ice, and then they have these spherical dim blue light detectors that they have on a cord. It's like a pearl necklace you took and draped it straight down, and you drop this string of spheres of detectors down into the water that you've melted into the ice, and then you hold the top end of that string and you let the water refreeze. The spheres are made to the point where they can take the compression of the compressing water, but now you have, and I think it's hundreds of columns of these detectors down hundreds of meters into the ice. And whenever any one of them detects that blue light, that's a neutrino. And since they have a matrix of these columns of detectors, if they see neutrinos being detected in a certain direction across the grid, they know to look in that opposite direction for the sky. So that's how A, they indirectly, not directly, detect neutrinos, and B, how do they know where they're coming from? That's how they do it. Japan is trying to stage their own neutrino detector. Now, you not only want to have a very sensitive detector, you also want to isolate that detector so it has no stray light whatsoever. In Japan, they're building their detector inside of a giant spherical vat of water in the core of a mountain. So they hollow out the inside of a mountain. They put this giant spherical container in there. They put all the detectors on the inside wall of the sphere, and then they fill the sphere up with the purest water they can get. And everything was going great until they had a minor earthquake.
Oh.
See, down in the Antarctic, they knew they were going to putting their spheres into water that was going to freeze, and you get compression from the expanding ice. So they knew to make the spheres extremely thick and durable. In Japan, they were thinking it's spheres in water. It just has to understand the pressure of the weight of the water at the bottom of the sphere, the container. They forgot to take into account shock waves of earthquakes in water. They had a huge setback about 5 or 6 years ago where they had a minor earthquake that affected the mountain. The entire sphere full of water went, and when it did that, the motion of the water created pressure waves, like back and forth inside the tank, and it smashed, I think it was 70+% of the spheres. So millions of dollars of setback.
Oh my God.
I think they pretty much replaced them by now, but that was just, we didn't think about that. So, but that's it. And there are actually neutrino interactions with molecules high in the Earth's atmosphere. They will produce the same sort of blue glow, much fainter and in like scatters. And they're actually, there's a professional astronomy program that is international that is building detector telescopes that will only observe with very large Earth-based reflectors for this blue glow. So obviously they're in very dark skies and they're only looking for that. And they've got different observatories around the planet that'll have multiple of these very specialized telescopes that they're just going to point almost upward, and it'll scan huge parts of the sky with detectors with very large fields of view. And therefore they should be able to see neutrinos occurring way up in the Earth's atmosphere, which gives them a much bigger detector than even Ice Cube is down in the Antarctic.
So they're looking for the Cherenkov radiation.
Yes, exactly. In fact, it's called the CTAO, Cherenkov Technology Astronomical Observatory. It's not one; it's just should be observatories. But they've just recently, I think this year, went from the prototype to the production design for the telescopes. So if you just do a Google scan for CTAO, I'm on their mailing list. It doesn't cost me anything, and I love reading all this stuff, so I subscribe to a lot of chatter. Any other comments or questions about TCrB? Okay, I'll stop recording.